All right. Hi, everybody. I'm Miguel Dickson. I'm from RoadBotics. I'm the head of data and I there. And thanks so much, Venture Cafe, for inviting us to do a little presentation here. And so, what I want to talk about is something that you guys have undoubtedly heard a lot about, but may not often get a very nuts and bolts practical explanation of. And that's basically how computer vision is used at a
At a
startup.
startup.
Oh,
Oh,
Emily, I'm getting a bit of echo feedback. I'm not sure if that's.
Did it go away just then?
I I think so. Yeah. Okay. Good. Sorry.
Okay.
Otherwise, that was
Sorry about that.
gonna drive me a little nuts. So with that, let me give you a little bit of introduction about my company and what it does, because I'll be using us as a kind of like an as applied case sample, case study. But then we can go afield and talk about other types of companies and similar work that they do if you're interested. And at any point, if you have a question, feel free to stop. I want to take this fairly informally and just kind of have an open discussion here. So what does my company do, RoadBotics? So the basic idea is that making maps for assets is really hard because lots of places have way too much to put on a map and way too little ability to do it without some kind of computer aid. So, as you might have guessed from our name, RoadBotics, one of our company's early kind of investments was in managing roads and road networks and kind of using AI to gather data about them, and I'm going to go into that in a little bit. But recently, we've been expanding into just more generally trying to help folks easily create digital maps that use AI in some way to help you manage that amount of data. One thing you might have seen us in the news recently, in this era of everybody talking about infrastructure, was that we did a joint report with the U.S. Chamber of Commerce to basically rate 20 road networks in America, right? And you can see the list here. And for each of these, we basically gathered data for a large amount of their road network and then used our AI to basically assess those roads and then produce it on a map. That ends up looking a little bit like this. I picked Philly. That was definitely one of our chamber cities, but I figured this might be an interesting thing to show you guys. Also, if you find our website, you can either find this on the chamber's website or on our website. But if you're actually here and looking at the report, this map is actually completely usable. You can dive in, you can click any of the individual ratings and see things that look like the photos at the bottom, and you can see why we rated things a particular way, and basically see, okay, this little snippet that I'm showing you is literally tens of thousands of images that all have been individually rated for how well that asphalt works. If you can imagine doing this by hand, like asking a civil engineer to take a look at a stack of 10,000 photos and tell you, how does this little strip of pavement look? Okay, how about the next 10 feet? How about the next 10 feet? Would be basically infeasible, and it's large part of why road network maintenance is kind of at not a great state right now, just because sometimes gathering the data is very difficult and costly. But there are AI techniques and specific computer vision that we can do to make things a lot smoother. I'll come back to this in a little bit, but I also just wanted to kind of broaden and say, okay, so how about things that aren't roads? Because roads are kind of a niche topic, even if a very important niche topic in infrastructure. So our general concept is that we're trying to basically allow you to go from assets in the physical world to what we call a digital twin. So a digital twin is basically saying, okay, I want a map that tells me where are my assets, where are my projects, what do they look like, what condition are they in, what stage are they in, how have they changed? Just all the kinds of questions that if you, for instance, were a DPW head and want to know this about roads or your stop signs or your fire hydrants or your pipes, or if you were a construction manager and you wanted to know, like, what does my site look like? Have we made progress? Does it look like the architectural plans? These are all things you might be interested in. So basically, this model has a bunch of advantages. One, it's a single source of truth. So for instance, if I say, I want you to go fix a pothole over near St. Bonaventure School, if everybody's looking at the same digital twin and the same map, there is no real ambiguity about what the problem is. You can collaborate, you can basically work more efficiently and not really have to resort to basically paper trails. Some of the types of data that we work with, right? So smartphone imagery, so you can just basically take a photo of something, drop it on the map. So say somebody busted a fire hydrant and you want to take a photo of it and basically add it to your city's map, you could do so. Right, photos. We also work with 360 photos and video data, so like GoPros, for instance. Right, this is basically a view of a GoPro image on our platform. Also, two-dimensional video, which is one of the most popular ways for people to basically aggregate and get data onto our platform. That's how we did the Chamber of Commerce study. Was basically using smartphones to take videos of the road, and then we break them apart into individual images, as you see on the map, and then our AI would rate them. And I'm going to talk a little bit about how the AI rating works, but here's just kind of an example of what it looks like when that video data has been ingested. And notice that this is the pre-rated data, so I'll talk a little bit about that, right? And just to give you an example of kind of how broad the types of techniques I'm talking about are, we can basically automatically pull out of your images any of these things. This is just kind of like a limited list. There's actually a few more things that we have in development, right? But they automatically get extracted out of your images and tagged. So for instance, if you take this photo here, you'll see that it's tagged with a crosswalk, a manhole, that fire hydrant, the water supply. Those things are all automatically tagged. And then I happen to know from personal experience that the 25th Street tag was manually added by a user. We, in fact, can't quite get to the automatically knowing that that is 25th Street, though there is a version that we can do. I can stop and talk about that. But lots of things that basically you can use computer vision to extract. And then that way, taking a photo of something becomes a very rich way to annotate a map versus like a very manual and kind of tedious way of annotating something. And then to see an example of how this works, basically, you see lots of assets that have been tagged in a particular user's map. And then you can see the way that they can kind of filter through and look for things. So say that somebody had said that there was a damaged sign. They could look, pull it up, see the sign, and be like, oh, that seems like it should be replaced. It's leaning substantially. It's going to fall over. Or say you're looking for fire hydrants here. You can see the fire hydrants. Or a rusty fire hydrant, missing things. This loop will go on for a while, so I'm going to skip it, but just notice that basically lots of aspects of how you would want to organize and think about your real world assets are all available basically with no additional work for the user, which is quite powerful. Right? And then I'm going to actually skip that. And then, so what do we use machine or computer vision for? A few things, right? One is the GPS localization. We want to basically get where is this asset in real space. But the focus of what I'm going to talk about really is the automatic extraction of assets, because in a sense, this is kind of where the magic happens. You say, okay, how do I go from taking photos or taking video or taking whatever to this being labeled a fire hydrant? Like that's kind of the magic key step of computer vision. And it's been our experience as a company that though folks are familiar with the idea that this works and that this is a technology that exists, they often don't really grok it. They don't really get like, how does it work on the inside? So my goal today is basically to give you a top level understanding of how computer vision works, such that if you wanted to dive in and learn more about the technical details, you would come from a pretty strong conceptual understanding of how it works. Or contrary-wise, you might understand like the extent to which this is or isn't magic, right? For a lot of folks, an insufficiently advanced technology is basically indistinguishable from magic, right? That's the Arthur C. Clarke quote. And computer vision for a lot of folks, I think, unfortunately, tends to fall into that it's magic. But I think once you see the explanation, you'll see it's actually kind of just a lot of work, but it's not super magic, though the insight might be. So that being said, let's jump right in and kind of go into like, how does computer vision work and how do we use it, right? So this is probably an analogy you've heard a lot before, but computer vision is a version of machine learning. And machine learning kind of works like human learning, right? The idea is you have an input and you have a trained machine and it gives you a particular output, right? So for instance, for rating the Philadelphia roads, what we want to do is feed it a picture and have that tell us, is this a good road or not? So that top left photo, pretty good. There's no real damage on this road. We want to rate it a 1, right? So on and so forth for the other images. But we don't want to actually do the work. We just want to basically give the machine a big dump pile of images and have it sort it, label it for us, and basically drop it back out on a map. A lot of the later parts are software work, but the computer vision part is saying, okay, what about this image means that it's undamaged road? And more generally, that's how most machine learning models work, right? You go from a set of inputs, and by the way, even if you think of something as, like a photo as one input, in practice, it's actually a ton of variable inputs. I'm going to go in a little bit of detail how that works. But you want some kind of output that transforms your inputs into something more useful, which is basically any machine you've ever thought of, right? Is going from something that is not immediately useful to you to something that is. So one example of this, and this is kind of how roads work, is this is our model for detecting undamaged pavement. As you can imagine, knowing that something is undamaged pavement is really, really important, right? A perfect road is basically a big chunk of undamaged pavement, and contrary-wise, a damaged road is basically a big area that is undamaged pavement. As you can tell, the image on the left and the image on the right are basically the same image, except the image on the right has had a model applied to it that basically tries to predict for every pixel in the image, is this pixel representing a piece of undamaged pavement? Yes or no? It actually turns out to be a floating point number between 0 and 1. A floating point is just a computer science representation for a decimal number. So one of those might be like 0.23, and one of them would be 1, and a lot of the top would be 0. And the idea is that we basically represent that visually by coloring it with a white shade intensity that corresponds to how likely the model thinks it is. So that you can see that the model is really certain about some of the stuff in the middle. And then a little bit off to the right, it's a little less certain that this is completely undamaged pavement. And you can see why, right? There's a little bit of abrasion and texture on there that isn't really undamaged, right? But the stuff off in the distance looks a little better. And the model has higher certainty about that. You can generalize this technique in what's called a segmentation model, right? And that means basically you want to do this, but you want to do this for a bunch of object categories, right? So you want to take the top picture and basically say, okay, which parts are road, which parts are sidewalk, which parts are building, vehicles, fences. You get the picture, but the basic idea of this model and this model is just more classes, right? You want to do more things, but the basic idea remains the same. So again, I've kind of told you a little bit more about how it works, but I haven't really explained how it works. So I want to dive in a little bit deeper than that, right? A model essentially is a math equation, right? So a math equation that you're all probably familiar with from Algebra 1, way back when, right, is a linear equation, right? And the idea is that you have an input, that's your x variable, right? And then you have two different parameters that kind of affect where it ends up on the y-axis, right? One of them is the slope, and one of them is the offset, or the y-intercept, right? And the idea behind training a model is basically you're trying to figure out what these M and B are for a particular set of data. So you've likely seen this in the context of like linear regression, right? Which is where you take a bunch of values, right? And then you ask Excel, hey, Excel, can you give me a linear regression on this so I can figure out what the pattern here is on the data? And I'm joking about the Excel part, but the idea here is that this is a really common technique, right? And it is an instance of model fitting. We don't really talk about it often, except in a math class, as fitting a model. But really, finding this line of best fit, this linear regression, is just a very basic form of model fitting. You're saying, okay, there's a bunch of data here, and the model that best fits, that best explains this data, is kind of a line that looks like this particular line, right? So how does this work for machine vision? Well, I alluded to this earlier, but the basic idea is an image is just a bunch of data points. So for example, a black and white or grayscale image, right, is a bunch of pixels that are arranged in a particular way and then have particular number values associated with their intensity, right? So on the left is like a very like pixelated downsampled image of Abraham Lincoln. You can kind of tell, right? It's got the famous beard and everything. And the idea is that for each pixel, and that this is like super blown up, in practice pixels are incredibly small, right? In practice, you can tell each one of these pixels has the amount of whiteness or blackness mapped, right? So that's why it's called grayscale. Grayscale is just a fancy term for a black and white representation. And for color images, it basically works exactly the same way, except in the most common model called RGB, for red, green, and blue, you basically have three different numbers for each pixel, basically denoting what mixture of red, green, and blue produces whatever color that particular pixel is. And this is what you're seeing when you're seeing a picture. There's more technical detail here about specific image formats and different color space models, etc. But the basics is it's just a bunch of numbers that tell you, okay, what should this picture look like when I add up all the colors and arrange them in a particular way. So much like before, we were trying to fit a model to a particular set of data points for a linear regression. What a computer vision model is basically trying to find a model that tells you something interesting about the collection of data points that is a picture, right? So your inputs here go to an output, right? But this particular type of thing, a neural network model or a computer vision model, most computer vision models are neural networks, so that's the kind that I'm going to focus in here on, but there's a wide variety of other types of models as well. But basically, when you break them apart, they're just individual math equations, but they're called neural networks because basically the idea is that you go from a lot of inputs. So, for instance, a high definition picture, a 1920 by 1080 like just standard HD photo, the kind of thing that you get when you take out your smartphone camera and take a picture of something, has a million-ish pixels in it, right? So that's a lot of inputs, right? Instead of your linear data model that has one X value corresponding to one Y value, here we would have millions of inputs, but you might want only one output. You might just want that 1, 2, 3, 4, or 5 road rating, or you might have a bunch of outputs. You might want a specific description of each pixel, in which case this is a mapping of like millions of inputs to millions of outputs. And then depending on the type of model you're making, you could pick different types of things. So for instance, if you were to look at our neural network model, it basically looks like this underneath the hood. It's a lot of equations. Each of them tells you something slightly different about about the image. One way of thinking about it is that there's one layer of the model, right, that is looking at each individual pixel and telling you something about it. But then there's actually another layer, another set of models that looks at basically what are called convolutions. And convolutions are a fancy way of saying a little bit of the area, right? So intuitively, if you thought, okay, if I had a pile of pictures and I wanted to pick out a stop sign, right? I might really quickly riffle through the images and try to find things that look like octagons. That way, just kind of lazy on the eyes, you're just looking for an octagon. Neural network models are very similar to that. You just learn a lot of representations of the data that help you pick out things that you're interested in, right? And they're called, I don't know if you've ever heard the term deep neural network models, but they're called deep mainly because they have a lot of hidden layers, right? So instead of being a simple equation where it's just like y equals mx plus b, there's actually sets of equations that correspond to each other. So this equation feeds something to this equation, feeds something to this equation, and you build them kind of empirically out of layers to see what works and doesn't work. And each of these layers is itself a type of model. So this is kind of like a turtles all the way down. It's just math all the way down. Specifically, nonlinear math applying to pixels or groups of pixels, right? So I'm going to show you kind of like a visual representation of a particular type of model, right? So imagine that these are the layers of a particular computer vision model, and it's what's called a binary classifier, but a binary classifier that we're going to use for semantic segmentation, right? So binary meaning it's going to say yes or no of a particular classification for a particular type of pixel, right? And then semantic segmentation, it sounds like a really fancy term, but it's a really basic idea, right? Segmentation just says, I'm going to give you a picture to this model, and I want you to break it apart into segments of individual things that have meaning. And the semantic part means I want a human label on them, not what the machine thinks about it. I want a label like person or purse or plants or grass or sidewalk, right? So if you see where I'm looking on the little person layer, that's the first one, you see how there's a bunch of ones that kind of outline a shape? That's because this particular model thinks that there's a person here, right? So this is all very simplified because in reality, this image on the left has hundreds of thousands of pixels. That's why it's like rich and deep. It's not just like, I don't know, this is like 15 across by 10 down. But the basic idea of what you're seeing is exactly this, right? Just at a larger and more intricate scale. So you can see the pixels that are 1 is the person, the pixels that are 2 is the purse, the pixels that are 3 are like plants and grass, the pixels that are 4 are sidewalk. They don't come out with those numbers. You do that at a later step. Each of the individual steps is kind of like a binary. It's like yes or no. Do we think this is plants or grass? Yes or no. Do we think this particular pixel is a purse? Yes or no. And then you aggregate them all into one big picture, right? And then this is just kind of a superset to kind of give you a better visualization of what's going on, right? And you can tell if we were doing it at this resolution, right? If our pixels are actually these big squares instead of much smaller pixels, this would be a pretty good result, right? It gets the lady in the picture pretty much right. It gets the plants and the grass all right. You can quibble a little bit about where the building starts and ends versus the sidewalk, but all in all, it's a pretty decent representation, right? And what we want is just something that's a much higher def version of that, right? So that we, instead of doing this version, right, we get this one, which is pixel perfect, right? We want to know each individual pixel, like where does the car begin and end? Or in our case, right, where does the undamaged pavement start and end? And notice, by the way, that this model here, this is a really nice, this is kind of like this is what you show audiences picture. It almost never works this beautifully in practice, right? It's very hard to get a semantic segmentation that is pixel perfect. Uh, but this is pretty much what data scientists look at all day, is something that looks like this, right? You want to get a model that performs like this or better, but this is kind of what it looks like under the hood, right? And then we come back to our original notion of like AI tagging, right? So if you pick a category here, so like let's say just the middle one, sidewalk. How does it work? We have a model that looks just like this, except instead of looking for undamaged pavement, it's looking for sidewalk, right? Or, you know, guardrails. Okay, same idea. We go to a picture like this, and we're looking for guardrails or cars or fences or the like, right? And that's basically it in terms of my kind of like overview. I'm going to stop here and go to QA, and depending on what folks are interested in, I can dive in and talk a little bit more in depth about the topics. Sorry, that actually went a little bit faster than I was expecting.
No worries. It's very interesting. Are there any questions from the virtual or in-person worlds?
Hi there. I figured it might just be easier to ask instead of typing it out. Quick question for you. So, hardware-wise, how much do you find there being better assistance in either hardware or image processors for the construction of some of this, for processing some of this data versus some of the code that you end up having to write to manipulate and generate these neural models?
I guess so. And correct me if I'm paraphrasing your question incorrectly. You're asking, in practice, does a lot of our time end up with the hardware that's kind of doing this work versus the software aspect of it?
That's a good summary, yeah.
So we have a little bit of an advantage here in that what we're trying to do is generally not real time. If you think about the speed at which local governments and municipalities work, where things are like measured in quarters, months, years, or 5-year plans, often in the case of pavement, uh, we do all of our work in offline batch processing. So we're able to basically try to optimize for speed, sorry, not optimize for speed, but optimize for cost and efficiency. So the hardware component of it tends to be abstracted a lot for us. But on the flip side, we care a ton about accuracy and not having many like false positives or false negatives, right? Because in this kind of application, bad data is like worse than useless, right? It's not only not going to help, but it could actively detract from somebody doing the right kind of work.
Yeah.
So in our case, it ends up being like 99% software, 1% hardware. And even that amount of hardware generally gets abstracted into public facing clouds like AWS or GCP. A lot of those make the hardware aspect of this pretty trivial for folks who aren't doing stuff in real time, which for us, we are effectively, from the government's perspective, doing things in real time because our analyses take like a couple of days to turn around from data ingestion to like the completed map, which for local governments is essentially instantaneous. But in the hardware world, that's really slow, so we can use cheap stuff.
Thank you.
Yeah, you're welcome. Good question. All right. Emily has a question. What other applications of this technology excite you about the future of AI? So one of the things I think is really cool about this computer vision type of technology becoming more easily accessible and cheap and kind of omnipresent is that a large part of I think what kind of is, especially in the government space, is unfortunate is that a lot of people's lived reality of what their city looks like or what their communities look like and feel like just don't seem to be accurately represented in the government space, right? And I don't think that this is a deliberate thing in the government space. It's just that these problems are overwhelmingly large, and Americans tend to be really skimpy on how well we provision our local governments. As you can tell, I'm very much a local government person. I like them getting good budgets and good funding, right? But one of the issues, right, is that data gathering is a really expensive and hard and kind of like specialized process, right? So I think we're not the only company that tries to do this and use kind of like AI to cut down on cost, efficiency, speed. We just have our own particular take on it. But I think as these kind of like AI techniques become more commonplace, I think the ability of governments and services to basically have much more power with basically do more with less is almost unbounded, right? Like for us, the idea of like providing a road network, right, was an incredibly expensive endeavor that cities did like uh, once every 5 years or once every 10 years. And usually the data quality was pretty bad and it took them months to compile. This became a thing that we can deliver to towns and municipalities in a matter of days. And honestly, if we wanted to put the money and it was worth it, we could probably turn it around in hours or minutes, right? It's just not worth it for those municipalities. I think what we are doing is just an example of what people are going to do for everything, such that it's going to be really easy for people to basically get and send data to their government and have it acted on quickly. It's no more like calling a 411 to report a pothole or saying like, all the street lights on our thing are down. I think the barrier to engagement is going to fall with better applications of the technology. Louis Padullo is saying, give the link to see the Philadelphia roadmap. Okay, if you give me 1 second, I can probably pull that up. I'm going to stop share for a moment so that I can share that link. So I'm going to just go ahead and put this in the chat. And then there's a few things you can do from this site. You can go straight and read the kind of like text version road condition report. But the map itself is also clickable. So here I can actually share my screen again and show you guys how this looks. Are you guys seeing the map right now?
Yep.
So if you click, right, this is kind of a mini example of our platform, right? So this is Nashville, but I can find Philly. Right. And this is the way our platform works. And you can kind of dive down and take a look, for instance. As you guys can tell, the model picked out a 5 here as very bad, and you can tell that there's a pretty gigantic pothole. It's not very deep, but it's certainly very wide. So this road is effectively broken.
This is very cool. I remember when I was in school, I worked with like ArcGIS. And it kind of reminds me of that in terms of just like you mapping and understanding our physical work, kind of breaking it down into numbers and better understanding it, through statistics. That's really cool.
Yeah, so ArcGIS is an example of this kind of like geospatial and map processing. But one thing is that it often requires a high degree of expertise to kind of put things into ArcGIS and make them like uh, easily publicly consumable. One nice thing about the kinds of maps that we do are generally that they're super low friction, low expertise kind of things. You feed us the data, and we do all of the work of getting it on the map, getting kinds of interactions like these tags, the searchability, doing these kinds of like road network analyses. And we think that a lot of work in the mapping and digital twin area is going to kind of follow, I don't want to say follow our lead, but be coming from a very similar place of what we're doing, right? Where it's less that you have to have a high degree of GIS expertise and a lot of data expertise to make these, but rather it should just be more like, okay, you gathered some kind of data, let our systems make sense of it and make it useful for you.
And I know that early you talked about that this making this data super accessible. Can you just talk a little bit about the importance of that, or like why you think the public should have access to all this data, and like what we should be making of it?
Yeah, so obviously my perspective on this is colored a lot by our interactions with local governments in the asset management space, right? So I think Mayor Pete was famous for saying that the pothole is every mayor's enemy, right? And in the sense of like, no matter where you are at a local government layer, people really care about issues that directly impact them. And oftentimes, asset management is one of those big areas. Like, for instance, and this goes across a lot of layers of just general societal equity, right? So, for instance, if street lights aren't working, that makes it much less safe for women and pedestrians in general, right? Like, that's just a more threatening, less accessible city. We're doing work with trying to automatically reconstruct sidewalks and their conditions, which is a bit of a harder problem and kind of involved in the 3D space. But that has huge accessibility implications, right? A lot of cities don't actually have a great notion of which of their streets or sidewalks are accessible at the moment, right? Even roads, which are relatively easy to collect data about, I mean, they're flat, you can just drive them, you can see what's going on with them. Sidewalks need a lot of modeling, right? You need to say, okay, can a differently abled person who's in a wheelchair like actually navigate the space? So if you think about like where local governments and municipalities are with even just the quote unquote easier questions like road networks, you think, okay, nobody's really happy. Very few people that I've ever talked to in my line of work are really happy with their municipality's handling of roads. And then you start looking at these second layer issues, and it's like, wow, we're really like, our ambitions are here and our capabilities are here right now. And I think there's just a lot of areas where uh, the improvement in these things is going to be, I think, really kind of crazy rapid. We're going to go from basically no data about these things to having really intricate data that will help us actually make really good decisions about these things. So stay tuned for sidewalks. I'm really excited about that. That's a project that my team is working on pretty heavily, and we think basically we can roll out relatively soon. But the idea will be the same way that municipalities can buy these kind of like road network analyses from us, they'll be able to buy these kinds of like sidewalk accessibilities. And then that actually flips the burden, right? Because currently under the ADA, you can kind of bring the complaint and say, this is not accessible. But there's very little kind of like operative burden of saying, we know that this isn't accessible and we have to fix it. But if you can bring the data, then all of a sudden the equities have flipped very rapidly. You can say, look, the city is performing really poorly on accessibility. Here's a map that shows you everywhere that this doesn't work.
Yeah, that's really powerful. And also, have there been any links between this research and the future of like self-driving vehicles?
Yeah, and we had a question from Chris about self-driving wheelchairs, which I think are still one ways off. One thing that we've actually found a little unfortunate is that, well, I guess the flip side is it's been fortunate for us as a venture-backed company that we don't have as much competition from autonomous vehicles, but just largely because they prefer to deal directly B2C, and we've been very B2B or B2G in terms of our focus. But yeah, we think autonomous vehicles and a lot of the sensor work that basically is being built into a lot of like cars that are coming out. Almost every car that you buy has like a good rear view cam, and a lot of them now have front facing cams as well. And those can basically collect the exact same kind of data that we use for our analyses. There's a lot to be said about the future in which cameras are everywhere and pointed at everyone at all times. And I think there are definitely some interesting like ethical and kind of societal structure issues that we don't deal with very well. On the other hand, there is a tremendous opportunity to actually understand our world better and try to do something productive with all those cameras and sensors that are pointing everywhere. So I'm in the camp of folks who are trying to use that data and that kind of like new richness of information capture to produce products, especially in the AI space, that actually do something useful with it.
Yeah, I think it's a great point because I think there's definitely a lot of fear and skepticism when you think about the amount of cameras that are everywhere and all this data collection, but it is very hopeful to me to hear about the ways in which they can actually be useful. I've honestly never thought of that. I'm just like, everyone's spying on us. But it is really useful to know that there are organizations who can take that data and make something more accessible, more beneficial to the community. So that's really awesome.
Yeah. One way I would definitely phrase that complaint is, how come there are all these cameras and yet the DPW still doesn't know there's a pothole right outside of my house, right? That's a
Yeah.
very incongruous kind of juxtaposition of like, how is there so much data for these purposes, but it seems so little practical use is being made out of them. And I think largely because the practical use is still waiting on other companies just like ours to come in and be like, we can use this data and get something really constructive and useful out of it.
Yeah, for sure. Are there any other questions for Miguel about any of the things that we've talked about?
We've got another question from Chris on the data collection site ReadRoads. Do you prefer to collect data with drones or vehicles? And then are there non-video sensors that are good practical data sources? So um, I'll split this question into a couple of pieces, right? Specifically with regards to roads, drones are sometimes a little bit tricky due to FAA issues and kind of like flying them overhead in traffic. You really don't want to drop a drone into the middle of city traffic. Like it's just not a way of playing friendly with existing traffic. So for those kinds of things, we've often found that just like an off-the-shelf GoPro mounted on the dashboard is an excellent data collection device. It's basically a rounding error for drivers don't stop. Yeah, that might be actually the fear I have. In terms of drone collection tends to be a lot more useful for other types of assets where it's sometimes impractical to take, like photos or a smartphone, or for like large area reconstructions or large area asset identification. So we have a potential pilot project with the USDA that is interested in basically doing tree counts. You don't want to go on foot and basically survey a forest if you can possibly help it, right? Drone imagery is a lot better for that kind of thing. So we've honestly found that um, drones have their own niche where they're really good sensors, but they also lack a lot of like ground level resolution data, at least the ones that are currently available and that you are allowed to fly over a city. Uh, but ground level cameras are very cheap and ubiquitous and capture lots of stuff, and they also have a very low barrier to entry, right? Even if somebody doesn't own a GoPro, if they want to buy and use a GoPro to basically map out some asset of interest to them, the basic cost to entry is zero, besides the actual cost of the GoPro, which then is also useful independently of our platform. It's not something that is like tied to our company. It's just, do you have a smartphone? Take video with that. Take pictures with that. Do you have or want a GoPro? Take pictures with that. And then the idea is, the easier you can make the data collection and the more ways that people can basically start bringing data onto the platform and basically figure out uses for it, or that we can help figure out uses for it once we know that a particular type of asset or data is interesting, right? So our road AI came out of early market research where we knew that this was basically a weak spot in how DPWs operated. They basically had this job. We have to figure out which roads are failing and how to use millions of dollars of budget, but their data is really bad. Usually, and I say this with no exaggeration, the state of the art for most DPWs, even in tiny towns, all the way up to not quite the size of Philly, but like relatively larger towns than you'd expect, is for folks in DPW to go out in a truck with a laptop or a clipboard and basically write down notes as they go along and drive the network. And then depending on their notes, that's what's going to get repaved or worked on. Plus or minus people complaining proactively, right? Calling 411 and saying like, hey, there's a pothole in front of my house. Can you repave it? That's pretty terrible. Like it's not a high bar to meet in terms of saying, look, just strap a camera to your car, drive around, and that way the analysis will be objective. We're trying to say, look, that's basically the model people should be thinking about in this space. Make the data collection easy, and then make the analysis of it also easy, and then leave the kind of in between, how do you get from easy data collection to easy analysis, to companies like ours.
Very cool. Any other questions? This has been really interesting. I feel like I've learned a lot partially because I knew zero before coming to this, so my knowledge has increased by 100%.
Glad to be
Does
of help.
anyone else? Yeah. Does anyone else have any questions, or Miguel, is there anything else you'd like to add based on other things that we've talked about throughout the session?
Yeah, so one question I have just for folks generally. So I know that a lot of folks in the abstract, are engaged in some way with the idea of like infrastructure, and I think everybody knows like we need more and better funding and infrastructure. But I have to be curious on my side, like how do you guys think that Philly does in terms of things like its road infrastructure? Can you guys talk about that if anybody has an opinion about it? Or how do you think America does generally? This is something I always try to ask audiences because almost everybody has a complaint about their local government about how well it does or doesn't do its work. But I often find it interesting to kind of ask folks like, how well do you think cities and towns are doing about these kinds of things? And do you see other like improvements along these lines, or does it feel like somehow 2021, but things are still kind of 1980s or 1990s tech?
I mean, I will say right off the bat that I think anyone that I've spoken to about this study has been very surprised how Philadelphia did that we did so well. They got pretty surprised. I also think it's interesting because it definitely also depends on the demographics of the neighborhoods. So I'm also just thinking of applications where you can, show inequities on another level, on a data-driven level of, where you have certain socioeconomic conditions of people living there, but that the government is also not supporting their physical infrastructure.
So yeah, that's a really interesting point, Emily. One thing that is definitely true about the chamber study, which I maybe should have added a bit of a caveat, right, is that relative to the kinds of things we do, this is a very small and very selective study, right? If you guys look at that map, you're like, okay, it's Center City. Like, come out to any other area of Philly, and you're not going to get that score. And that was more or less true of a lot of the cities, just because again, this was a very new thing for the chamber to try with us. We're a small startup company. We weren't like a known national player at the time that they basically took a gamble on us and said, let's try this newfangled AI thing and get a bunch of ratings, right? One thing that I have definitely found is that you can almost infer uh, demographic or socioeconomic status on the full road networks, right? So most places that buy our service don't get these little like 50, 70, 80-mile chunks of their city. They'll do the entire city, or they'll do their entire road network. And oftentimes you can definitely see patterns of like, oh, this area doesn't really get the same services. Its roads are significantly worse. This neighborhood is significantly worse. This area is brand new and looks like it has been repaved even more recently than that. That's weird. My webcam kicked out there for a moment. So one thing that we'd definitely be a fan of is doing this study, but like at the full scale, right? Philadelphia's road network is significantly larger than the 70 odd miles that we did for the chamber study. And I think the same is very much true of almost every city that we did. It's a partial picture. It's not really the big picture, the entire picture. Some of our case studies are kind of interesting on that. You can see on our website, like we did the city of Savannah, and they were very pleased with it. And we did the entire city of Savannah, and then that kind of had some interesting kind of like side effects. And one thing I think that I want to note, because I feel like this might be getting into cynical territory, and I don't want to be cynical about this, is that oftentimes these aren't so much like a deliberate equity thing. It's just a kind of misequity of defaults, right? You hear from some people and they're in a position that they feel entitled to complain about it, or they have time, or they have the ability, or they even know who to tell that they have problems, right? And this kind of thing happens. But the folks who work at DPWs and who deal with these kinds of assets, in general, local government, is not the most glamorous, prestigious job. You get people who are highly publicly motivated, and they're public service workers. They want to do the best job for their communities they can. They just don't often have good tools to do it, right? One of the things that we found that was most interesting was that folks who had gotten our network study said, this is great because this takes all of the politics away from it. I can look at my road network on your map. I can filter it based on damage. I can draw up a rational plan that says, here are the areas that are most badly damaged. It makes perfect sense to do these two roads that are both damaged next to each other, whatever. And then I can present that to my city council. And what are they going to say? Like, I've got the images right here. I can prove that they're damaged. I can give them the map if they want to look at it for themselves and try to argue with me. But it takes a lot of the kind of like bad areas of politics completely away, because they were only there in the absence of stronger data and a more compelling visualization for saying, this is the work we should be doing. I think that's often also true in the kind of like disability and kind of like mobility access space, is that the arguments feel very abstract because people don't have good enough data to say, this is the work we need to do, this is the extent of it, like here's where we make the plan. A lot of folks who buy our service are very pleased to get budget increases, because then the town says, we had no idea our roads were in this bad a condition. Like, everybody knew their little neck of the woods had, you know, a bad pothole here or there. But once you can actually look at a complete data set that's recent, and this data is like taken 2 days ago, a week ago, there's no arguing with it, right? It just makes the policy decisions a lot more straightforward and a lot less contentious. And I think that's one of the areas where AI analyses and data analyses that are done by third parties like this will improve local governance, is by basically taking a lot of the squeaky wheel syndrome out of it and saying, no, this is just like, the data speaks for itself, at least until cities get into a lot better managed state. You know, there's just so much low hanging fruit that we'll instantly find for you and make these decisions much more straightforward.
Definitely. I saw Chris put in the chat that there should be a grant to scan the roads of low income zip codes, which, yeah, definitely.
Agreed. Yeah, I think, or just in general. And again, this is when they find the funding to use our services, it's almost always the entire road network. The DPW doesn't want to exclude folks. They want to know the picture. They want all the data. Nobody has ever come to us and said, we'd like you to not like collect the data for this area or that area. And honestly, if it came to that, we would probably have some very serious ethical discussions among our leadership team. But it turns out in practice, this never happens. Everybody wants the entire picture. They want to make these kind of like low politics, high policy kind of decisions. They just haven't been able to. It's a very difficult job, right? Especially if you're going from we're upgrading from trucks and a clipboard to a map that has basically GIS capabilities and that you can sort and filter and do all kinds of things with. Easy peasy after that.
Yeah, definitely. All right, well, we have a little bit of time left. Do a last call if there are any questions or any other thoughts on Philadelphia's infrastructure. Any thoughts about that?
Hey, Miguel. Again, just jumping in via voice, thought it'd be faster than typing it in. Because we don't have several hours, I won't go on about Philly's infrastructure. So I'll have a more general open-ended question. Considering that, especially you guys in particular, that you do a lot of the batch processing, have you ever considered crowdsourcing some of the video collection? Like you said, some of it's really accessible, you know, put a GoPro or a dash cam perhaps in a vehicle and then, you know, turn that over and off you go. What have been the thoughts about that?
Yeah, so in full candor, I'm always waiting for somebody to ask me about crowdsourcing. I literally, something about the concept of what we do always suggests crowdsourcing to people. And it's funny because it works really well and it also doesn't work at all. And so I'll tell you the kind of combination about how it works really well and it doesn't work at all. And it actually gets to both the equity and completeness issue. So our company, from its onset and periodically, we've tried different experiments to try to get the crowdsourcing thing to work. And what we end up with is somewhere between 70 to 90% of the road network we get exquisite, super reduplicated coverage of, right? Everybody has a cam and everybody takes video and we get perfect coverage of that area times 10 times 100, right? Like we'll get, you know, Main Street will have 100 different views of it from different people.
Sure.
And then there are neighborhoods. And again, sometimes this goes to like the equity and access issues, but that will get no data. Nobody will know that we exist. Nobody will know that they could take the video or data, and nobody goes out there. And one of the things that ends up doing is kind of implicitly corrupting the data. And I don't want to say explicitly because nobody's actually damaging the data in a sense, but it's kind of
An implicit
bias issue. Yeah, it's an implicit bias. It's perfectly stated. It is a bias that exists because instead of getting one snapshot that is kind of temporally in place and done at the same time, same quality, same everything, you'll get some areas that are kind of like the squeaky wheel in this scenario where they get lots of coverage and we have a great idea of how good a condition there is. And then there's a neighborhood that nobody's collected data for in years. And then that kind of perpetuates the problem of the incomplete data set in the first place.
That's something, for what it's worth, it's something that I think Waze addressed way back when they were first starting out, where they actually incentivized, it was all non-monetary points and whatnot. They incentivized people on driving roads that no one had been driving on before, so they could build their own map data before they picked it up from somewhere.
Yes, there are definitely econometric models of how to do this. They just never quite worked out for us in terms of it was almost always cheaper in practice and more practical to get local experts, and in this case, the DPW or the head of public works or whatever are essentially local experts for our case to do it. And then the snapshot timing is a lot lower. I think once we reach a certain scale, once we become like Airbnb or Waze size, cross my fingers here, the crowdfunding is something we'll return to for similar reasons. But it just turned out that, especially when we want to be able to say, within a certain time period, you will have a complete map. Even with the incentives, it becomes very hard to kind of have that certainty about data sets or completeness. We'll say like, we'll probably have 99% of your map probably within X many weeks. And for local government, that's really a not pleasant place of uncertainty, right? They want to pay for a service that just works. And basically, we can tell them once you are done collecting your data, you are done, just finish, if that makes sense, right? So there's kind of a simplicity of model thing there. Waze is a free best service kind of thing, right? Like just give me the best estimate that you have about like the conditions, right? So they're not really under an obligation to capture the entire network, but we always have been from the very beginning.
That makes sense.
I have a question from Louis about, do you give updates to clients? Give is an interesting term here. Yes and no and maybe. And the idea is that most of our clients try to sign up for like multiple year things where they will get like what we used to call it a scan, but basically they'll do AI road assessments every year or every 2 years or on whatever cycle makes sense for them budget wise. And then that'll basically be like a full snapshot refresh. With our newer platform, you can actually do this in a more piecemeal manner, but we always suggest that people do the entire road network. Places that are in the Northeast or have a basically, or in the North that have a freeze thaw cycle, often find that a year's data already is slightly inaccurate because a freeze thaw cycle where basically rain will get into the roads and then freeze and then basically crack the surface of the road or cause potholes that way often means that even a year's out data can be inaccurate with respect to saying that some roads are still good where they aren't anymore, or that some roads haven't gotten a lot worse over the winter. So the number of updates kind of that a particular client wants or needs is often tied to geography and local weather and local conditions.
All right, well, we just have a few minutes left. I'm out of questions. We've had a really wonderful discussion, and like we really appreciate you bringing so much knowledge to the table and just sharing all this insight with us. Do you have any parting words in the last few minutes for us to consider about the future of robotics and of AI used in this way?
Yeah, so if I had a parting thought, I would say, it kind of goes back to that earlier point about the cameras and the data sensors are going to be everywhere. I think it feels kind of pessimistic to say this, but I don't think there's a very plausible future in which those sensors and that data isn't there, or in which AI isn't there, right? It's kind of one of those, the ball has been rolling on AI technology for some time now, and it seems impossible to rewind in any meaningful sense. So I think one of the best things we can do collectively is to try to find ways to harness this kind of technology to produce very tangible gains, both in governance and then also when we can in equity areas. So, data for the good, I hope.
I love it. Well, thank you so much, Miguel. This has been a really wonderful session. Thank you so much to everyone in person and virtually who have attended tonight. or I guess this evening. And have a great rest of your day, everyone. And thank you again, Miguel.
My pleasure. Thanks, guys.
Bye.